Hello students, how are you? So we will start a new chapter, that is thermodynamics. So thermodynamics is very important from the exam point of view. So let us see that what are we going to cover in today's lecture. So these are some key concepts that we are going to see. So first of all, we will see what is system and surrounding. Okay, what are the laws of thermodynamics? What is entropy, gas free energy? So these are some important key concepts that we will go throughout our lectures, right? Spontaneous process and equilibrium. Okay, so these are the things I will go through. Now, why do we need thermodynamics? First of all, okay. So first of all, whenever a chemical reaction occurs, there is a release of energy, or there is a you can say absorption of energy, and this release or absorption of energy is kind of important to determine the reaction spontaneity. Okay, whether the reaction will take place or not. Clear? So if I talk about any reaction, whether it is a you can say if it is an electrochemical reaction in which you are converting a chemical energy into electricity, or you are converting electricity into chemical energy, right? So in all of these transformations, we are going under temperature change or heat change, and to study that we have this thermodynamics. Clear? Okay. Now basically what is thermodynamics? If you want to just define it, so it is basically the transformation of energy and their relation to heat, work, and temperature. Okay, so how does this energy is used in heat? Okay, it's producing heat, or it can do the work, or it can help in raising the temperature. So it basically deals with a macroscopic system involved a large number of molecules. So this is the very good approximation. So we don't get into the molecules, that what is the effect of molecules of temperature. So we don't get into it. What do? We just study the macroscopic system without bothering about the microscopic system that is being changed. Okay, so that is the way we do the approximation in thermodynamics. Clear? So this laws of thermodynamics apply only when a state is in equilibrium, or from one equilibrium state to another equilibrium state. So this is very important, that the laws of thermodynamics is only applied when a system is in equilibrium, or it is going from one equilibrium to another equilibrium. Then and then only the laws of thermodynamics can be applied. Clear? So what information do we get from thermodynamics? So these are some piece of information. These are some questions we will try to answer throughout the lecture series. So first is, how do we determine the energy change involved in the chemical reaction or process? So how do we know it? So, and when we know it, then how we will use it to confirm that our reaction will happen or not. So what are the factors that drives the chemical reaction? And next thing, to what extent your chemical reaction will proceed on the basis of the given conditions, okay, chemical conditions. So as I have told you, so we will discuss the energy change during a chemical reaction. Okay, so we will study that, and in that we have to study first of all some terminologies. So first of all, what is system? Okay, what is system? So system is basically defined as a you can say as a vessel, or you can think of it as a space where the reaction is taking place, and this space is kind of isolated from the rest of the universe. Okay, now the rest of the universe from which your system is isolated is called as the surrounding. Okay, so this system plus surrounding makes up the universe that we know. Clear? So it is kind of very abstract thing. So just take a bottle. Okay, if you just take a bottle and you suppose you do a physical reaction, not a chemical reaction, you do a physical reaction of changing ice into water by slowly slowly melting it. Okay, so what will happen if you just close the vessel at that point? Okay, so that will configure the system, or that will define the system boundary. Or you if you don't want to close, then in that case the system will be open, but still we have the boundaries. Okay, because it is kept in a tumbler, not tumbler glass. So tumbler will have valves, and that will act as a boundary. Now within the boundary we have the system, and outside the boundary we have the surrounding, and that total makes up the universe that we know. Clear? So the boundary that separates the system from the surrounding is called as boundary. Simply it is called as boundary. We don't have a specific name. It is simply called as boundary. So if you just want to just mathematically represent this whole system, okay, or just whole universe, you will simply represent this in terms of system and remaining universe. So U is equals to R plus S, where U is the universe, the system is S, and the remaining universe is R. So this is the mathematical expression for expressing the system surrounding and the what and the universe. Okay, clear? Now we have a system here that has been kept. Okay, so this is the system that we're talking about. So here is the wall or the boundary, and this is the surrounding. This green part is surrounding, and inside the blue part it is written system. So this one is system. So the first case we are taking is that it is an open system. What is the meaning of this open system? It is simply that we can exchange energy and matter between the system and surrounding. That system is called the open system. Clear? So if you are burning, suppose you take this beaker and you start burning paper inside it, right? Now this paper will be converted into ash and it will release some gases. Now these gases will go out of this vessel. Okay, so they are free to move out of this vessel. That is the reason they will be considered as open system, where the energy is already what is being done, that energy can be exchanged. Now suppose these ashes are manually kept out of this box, then the mass is also exchanged in the system. Then we can say completely that this is a open system where we have the access of what changing the mass and energy both. Clear? Or exchanging the mass and energy both. So this is the open beaker that we're talking about. So here the boundary is imaginary surface enclosing the beaker and reactant. Clear? Next is our closed system. So in closed system, what do? We just put a lid upon this beaker. Now your particles cannot escape, of course, but at the same time you will what will happen? Particles cannot escape, but the energy can be exchanged because we are not taking the thermal walls. Therefore, the matter cannot be exchanged because it is already closed. The container is already closed, but the temperature can, or you can say the energy can be exchanged. Now the presence of reactant in a closed vessel made of conducting material. Okay, so this is the example of closed system. Closed system. Now what upon the isolated system? So in isolated system, we take the boundaries such that the energy also cannot be exchanged, and plus the mass cannot be exchanged because we have put a lid here. And that system is called as isolated system, in which both the mass and the energy are conserved. Clear? Next is the state of a system. So what is state of a system? So state of a system is basically a way of defining the system. So initially you have studied the state here in the structure of atom also. So when we said that, okay, this is the wave function, and this wave function determines the state of the electron. So it says about the energy, okay, and all those things. So state means what? It is basically the information about the system that we are dealing with. So if you're talking about the state of the system, then we can talk about its pressure inside it, we can talk about the volume inside it, or we can talk about the temperature inside it. And all this are what? All these are basically the state of the system. We need to describe the system by specifying it before and after the change. Clear? Now, the state of a thermodynamic system is described by the measurable or macroscopic bulk. Okay, macroscopic properties. Clear? So in this way, if you know the pressure, volume, and temperature, we can determine the state of a system. So these are called as state variables. Okay, what are they called? They are called as state variables. So what is state variable? First of all, if you just define it more, then there are two types of variable: path variable and state variable. So state variable are those whose values depend upon the initial and the final values only. Clear? But it does not upon the values in the middle. Okay, so they are called as path function, and this is called as state function. So in order to completely define the state of a system, it is necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends upon the nature of the system. Clear? The state of the surrounding can never be completely specified. Fortunately, it is not necessary to do so. So what it is written here, that you know that this amount of heat is lost by the system. We don't know that what is gained by the surrounding. You can't approximate it or calculate it, and that is also not necessary to do because we can gather enough information from the system change only. Clear? Next is internal energy, which is also a state function whose values depend upon the initial and final values. Clear? So when we talk about our system, we talk about losing or gaining energy. Okay. Now all form of energy, the total energy of the system that we talk about, are called as the internal energy, which is a state function. So this internal energy can be sum of electrical, chemical, mechanical, or any other type of energy. Okay, so these are called as internal energy, in which we can take sum of any type of energy. Now in thermodynamics, we call it as U. We call this what? As U. Now suppose your heat passes into the system, okay, or the work is done by system, or matter enter or changes, enter or leave the system. In all these cases, what happens? In all these cases, you will see the what? You will see the change in internal energy. Why? Because internal energy is basically the overall energy. Now three systems, as we have classified accordingly, we have studied. Okay, so we have studied these three systems here. Now let us talk about work. Okay, let us talk about work. So suppose, let us examine a change in the internal energy by doing work. Suppose we are changing, we know that we can change the internal energy by heat, by work, okay, or by changing the mass. Suppose we are doing it by work. So if we do a work, okay, so let us examine. If we do a work, we take a system containing some quantity of water in a thermos flask, okay, or in a insulated beaker. Now what will happen? There will be no exchange of energy or no exchange of heat between the system and the surrounding. We call this type of system as adiabatic. What is the meaning of this? So if your walls are able to what? Say it is able to disagree with the allowance of, say, what? Heat, then we call it as adiabatic wall. Okay, we call them as adiabatic wall, and the manner in which the state of system may be changed will be adiabatic process. So if you are doing adiabatic, if you are taking adiabatic wall, okay, if you are taking adiabatic wall, then the process is also called what? It is called as adiabatic process. Clear? Okay. Now adiabatic process is in which there is no transfer of heat. We have said this. Hence the wall separating the system and the surrounding is called as adiabatic wall. So this is the wall. So it is a kind of adiabatic wall that rejects the energy exchange. Now suppose we are doing some work. Okay, we are doing some work on the initial state A, which is at temperature TA. Okay, and at that point we are considering the energy as UA. Now if you do some work, of course your internal energy will change, means UA will change, right? And the temperature will also change. Suppose it is at TB. Clear? Suppose that work we have done is 1 kilojoule. So therefore the change in temperature will be TB minus TA. Okay, so first thing this. Okay, so if you want to calculate the change in internal energy, it is very simple. Calculate del U is equals to UB minus UA. So in this way we can calculate the internal energy. Clear? What is the second way? We can do an equal amount of work. Okay, we can equal amount of electrical work with the help of immersion rod and note down the temperature change. Clear? Then what we will do? So this is the change in temperature. So in fact the experiment in the above manner were done by the JP Joule between 1840 to 1850. The same experiment of calculating the temperature change was done by the JP Joule, and no matter how it was done, it gave the same state. Okay, means the internal energy was not changing. Of course we were changing what? We were changing the function. Okay, but still we are not seeing any change. So it is irrespective of path. Or we can write it in this way. Suppose you are taking adiabatic wall, then the work that has been done is the work on the system, and it is the only energy change, means it is the only factor that is responsible for energy change. Therefore the change in energy is equals to W adiabatic. So we have written it W adiabatic, means it is adiabatic work. Clear? Now therefore we know that internal energy is now a state of system. Now if you talk about the IUPAC, so if something is losing energy, then that will have a negative value of U, and if something is gaining energy, then it will have a positive value of U. if the work is done by the system, work adiabatic will be negative because system is doing the work, so it will lose energy. Okay, so that is the what? That is the negative energy, right? So suppose, can you name some other family state function? So some of the other families are VP, and VP and T. Again, we can have 25 to 35 degrees Celsius. So if you bring a change in temperature of 25 to 35 degrees Celsius, the change in temperature will be 10 degrees Celsius, right? Then how can we calculate the final temperature? So the T is a function of state function, and change in temperature is independent of the root taken. Therefore, the volume of a pond, for example, is a state function. Again, the volume is also what? A state function. So these are all what? State function. Either by rain or by tube well or by both. Next way that we can change the energy is the heat. So if it supplies heat or if the system loses heat, then in both ways you can get what? You can get exchange energy. Clear? So let us consider bringing about the same change in temperature. Okay, about the same change in temperature. So initially we are changing different things. Now we are changing the temperature. Okay, so by transfer of heat through thermally conducting valve instead of adiabatic valve. So in this way we can provide heat. Okay, so what we have taken? We have taken a closed system in which we can provide heat. So initially suppose our temperature TA. Now after it is enclosed in that, suppose some heat is supplied that makes the energy TB. Therefore the change in energy will be TB minus TA. So in this case the internal energy is Q because that is the amount of heat that is transferred and it is changing the energy. Similarly, in previous class it was what? It was work. Okay. Again, by convention, if you are losing heat, then we call it as negative, and if you're gaining heat, let us call it as positive. Now the internal energy system increases and Q is the negative when heat is transformed to the system or the surrounding. Clear? So this results in a decrease in the internal energy. An earlier negative sign was assigned when the work is done on the system and positive sign when work is done by the system. So this is still followed in physics book, but the IUPAC it is reverse in case of what? Chemistry book. We have a different convention that if work is done by a system, then it is negative. It is done on the system, then it is positive. Now we will talk about this first law of thermodynamics in the next class. Okay, so we have already talked about what is Q and W. So just let me give an idea about this. So what I am telling here is that we have seen earlier that the amount of internal energy can be changed in either two ways. First is if you are changing the heat or if you are exchanging the heat, or second one is that you are changing the work or you are doing the work on the system. So in that case, in that two cases, we are changing the internal energy. So we can say that if both are the only factor, then that internal energy change depend upon only two factors, that is heat and work. Okay. What are those two things? That are heat and work. Clear? So we can write it as delta U is equals to Q plus W. Clear? And it will only depend upon the initial and final state, and it will be defined and it will be independent of the way the change is carried out. Clear? So if you talk about the adiabatic work, okay, if you talk about the adiabatic valve, then what will happen? Q will be equals to 0, right? And suppose the work is also not done, therefore del U is of course 0. Clear? So this is the mathematical statement of the first law of thermodynamics, which says that energy of a system is isolated. So with this, we have seen something about first law. We'll consider, we can discuss more about it in more detail in the next class. So for this, it is okay. So thank you for your time. With this, I end my lecture.